Hello everyone. In this video I will show you how you can use bagging to reduce the variance of the predictions when using a decision tree. We will start with generating a dataset. And here you can see the data. In this last line, line 6, we start from the y data, but we standardize the data such that we have a mean 0 and a variance equal to 1. This will be the training dataset. We will use a decision tree and this training dataset to fit our model. Then we will apply that trained model on a test dataset and determine the root mean squared error to see how well the fit is. So we also need a test dataset. We will use the training dataset and the decision tree. So for the decision tree, we will first fix the controls. So we have here the number of observations in our training dataset, the minimum node size and the deviance that you need to continue with splitting the feature space in different nodes. I take this very small and I take here one because I want to grow a large tree, a tree that almost perfectly fits the training dataset, so it will overfit the data, but then by aggregating many trees we will get rid of the overfitting. So let's first start with determining the test error when using a single decision tree. With this code, I will calibrate the tree. Then I will make predictions using this calibrated model and using these test observations. And that you can see here, we use the predict function where my new data is now the data in the test dataset. Because my model uses a feature X, I need to create a data frame with name X. So F1 are the predictions. I will then determine the root mean squared error on the test dataset using the predictions in F1. And that root mean squared error, I will denote that by S1. These are your squared errors. We will sum all the squared errors. We will take the mean, so I can directly take the mean. So sum and divide by the number of elements you have. And I have a root mean squared error, so I take the square root. And then I want to show the output. So if I run this, and then we see that the root mean squared error is 0.40. Let's have a look at our dataset and the tree that is fit on that dataset. So the test dataset is this dataset. This is the test dataset. Now I will put in this plot the predictions F1. You see that the circles are the test observations, the blue dots are the predictions. Let's have a look at the fit on the training dataset. So this is the test dataset. Let's see what happens if we predict our training observations. So here I first plot the XY values, the training dataset. Then I fit my tree and I directly apply the predict function without specifying the new data, because in that case R will just predict in the training X values. So if I do this, what you see is that there is no difference between the observations in the training data set and the predictions. We can make the plot a little bit more clear to see what happens. So I make the observations in red and a little bit bigger. And then you see that all my predictions, the blue dots, are exactly in the circles, the data. So I perfectly fit my training data sets, but I have problems with fitting the test data set. And that is exactly what we mean with overfitting. Your decision tree is too much aligned with the training data set and it cannot fit the test, the new data set, very well. If we have a look in the model, so this is the decision tree, and let's look into the summary, then you see that that regression tree is a very large tree with 98 terminal nodes. So you make a very large tree and that overfits your data. So we now try to use bagging to get rid of this overfitting that you see here in this plot. B is the number of bags, the number of individual decision trees that we will use. F dot I will be a matrix where in each row of the matrix we will put the predictions of decision tree I on the test data set. So F dot I is a matrix with the number of columns equal to the number of test observations that we have, and the number of rows is equal to B, because for each test observation we will have B different predictions. So I now make a loop where in each step for each I going from 1 to B, I will fit the decision tree, make a prediction and put it in a row of F dot I. In order to make the prediction, I will generate a bootstrap data set. So D dot I will be the numbers of the data that I will put in my bootstrap sample. So as you can see, I have 100 observations in my training data set. I will randomly sample out of these 100, again 100 observations, but I replace each time the observation that I pick. For example, if I run this, then a first bootstrap sample contains these observations that you see here. If I know the number of the observations that are in the bootstrap sample, I can define x.i, y.i as my bootstrap dataset. Now I will predict the test observations, but I will calibrate my decision tree not on x and y, but on x.i and y.i. So we can use the same code as before, but now I'm not going to use y and x, but y.i, x.i, and my new dataset has as input feature variable x.i. And all these predictions are stored in the ith row of my matrix f.i. So we can look at the dimension of f.i, and you see it as 1000 rows, because B is 1000. It has 100 columns, because my test data set has 100 elements. We now have to determine our bagged decision tree, and for example, for the first column of f.i, the first column, all these values here are predictions for the observation where x is equal to 0.02. So I have different decision trees based on my bootstrap sample, and then based on this decision tree, this is my prediction. But sometimes this is my prediction, and then it jumps to different values. So what will be my final prediction for this test observation? It will be the average of all these individual predictions. So it means that going from f.I, the matrix with all the individual predictions, to the back decision tree, I have to take the mean for each column. And I put these predictions in the vector ff. And then you see ff are all the predictions for my test observations. And then I can again determine the root mean squared error of these predictions. The root mean squared error is now 0.35, and S1 was the root mean squared error of the individual decision tree, which is larger, it's 0.40. So by aggregating 1000 individual decision trees, I end up with a better fit for my test dataset. Let's plot the observations of the test dataset, the predictions of the individual tree, and the predictions of the back decision tree all in one plot. So in this plot, the circles are again the test observations. The blue dots are the predictions of the backed decision tree. The red dots are the predictions of the single decision tree. And for example, you see that the individual decision tree has these large values here, which are reduced by the backed decision tree. The backed decision tree is a bit better in predicting in this region. And you see that the better performance of the back decision tree is reflected in this root mean squared error. A single decision tree was overfitting the data. If we apply that decision tree on our training dataset, there is no difference between training observations and predictions. They completely match. Let's see how that same plot looks when we use the backed decision tree. So we are going to apply the back decision tree on the training dataset and put everything in a plot. So we start with creating a new matrix that contains on each row the predictions for our training observations, and we have 1000 rows because we aggregate 1000 individual decision trees. In this plot, the circles are again the training observations, the blue dots are the predictions. And you see that now we are not overfitting the data. It's not the case anymore that we perfectly replicate our data set. So by aggregating many individual decision trees, we got rid of the overfitting in our decision tree. Note, however, that in this f.I, you have on each line, on each row, you have an individual decision tree, and in total we aggregate b individual decision trees. Each of these individual decision trees is overfitting the data, but if we put them together, we get rid of the overfitting. In this simple example, I showed you that by using bagging, we can reduce the root mean squared error of the test data set. However, I just picked a value for b. I aggregate 1000 different decision trees. What I want to do now is I want to see the effect of b on the test root mean squared error. So remember that in f.I, on each row you have the predictions of one single decision tree. And then if I want to have a backed decision tree with 1000 individual decision trees, I just take the mean over all the columns. But if I want to have a backed decision tree with only 500 decision trees, I can start from this f.I, but only average over the first 500 decision trees. So by doing that, I can have the prediction of a backed decision tree with b equal to 1, b equal to 2, b equal to 3, and so on, by, in a cumulative way, averaging over the columns of f.I. That's what I will do now. So ff.CumSum is the same as we had for ff here. It's the mean of all the columns, but now I'm going to do that in a cumulative way. With this function, with the apply function, I will start from a matrix f.I. The 2 means I'm going to apply a function over the columns of f.I. And which function will I apply? It's the cumulative summation function. So for each column, ff.CumSum takes the cumulative mean. However, if I, for example, in ff.CumSum on the 5th row, I have the sum of the first 5 rows. If I want to turn this sum into a prediction, I have to divide by 5, by the number of elements I had in my sum. So that's what I do in this second part of the formula. Here is the sequence from 1 to 1000. If I now do repeat, and I repeat that how many times? Length x dot test, then I'm going to repeat this vector of 1 to 1000 this many times. And then I store that in a matrix. And if you have a look at that matrix, you see that it is a matrix with on the first row 1, then 2, then 3, then 4, all the way to 1000. So I have to start with this cumulative sum and divide the first row by 1, because it only takes a single decision tree. The second row of this cumulative sum I have to divide by 2, because you have a sum over 2 elements, then I have to divide by 3, and so on. So now in ff.CumSum, I have on the first row the predictions for the test data set using a single decision tree. On the second row, I have the predictions for a back decision tree with 2 decision trees. Here a back decision tree where I aggregate 3 decision trees, and so on. So now I take the root mean squared error using the predictions on the first row, then the root mean squared error using the predictions on the second row, and so on. We start with the predictions. And for example, we have to subtract all the y test observations if we look at the first row, but we have to subtract the same test observations if you look in the second row. These are different predictions, but different with the same test observations. So I want to create a matrix with the same dimension as this one, but where I have on each row the y.test vector. So this is the matrix with all the test observations. I take the difference prediction minus test observation to the power 2, the squared differences. This is a matrix with squared differences. Then I need to take the mean over the rows to get the root mean squared error of my first set of predictions, my second set of predictions, and so on. And if I have the means, I have to take the square root to get the root mean squared error. And here you see the plot. And you see that if we take only a few decision trees, we get a large test error, and that test error gets smaller and converges when we increase the size of our backed decision tree. Let's now have a look at how well we can approximate the function of our training data set. So if you have a look at the data, you see there is a clear functional relationship, this sine function, and you have the variance around the function. Let's have a look what we can do. First of all, we are taking the x values from 0 to 10, and we are going to predict y values for all these x values, put them in this plot and connect them with lines to see what kind of function we can generate with the decision tree. I take 1000 different individual decision trees, and I again do the same code as before. I construct a matrix, and then I bootstrap a data set, do my predictions, and put it in a certain row of my matrix. And this is what we find. We have our data sets, and we have this function that maps x on y. And what you see is that that function is not really smooth. And actually in this case, we know what the function should be. So we can plot in green the true function that we try to reconstruct. We have the red function, that is the function that comes from the back decision tree. We have the green function, which is the true function. And the problem is that we do not get a smooth function. We call the Gauss process regression or the kernel ridge regression. There we are able to create smooth functions. So what is going on here? The problem is that if we look at this step here, we create a bootstrap sample d.y and the x and y values using the bootstrap. However, we shuffle the observations in our training data set, but of course it's not that surprising that x.y and y.I are very similar to the original data, and if I create two different bootstrap samples, then of course the data sets are very similar. They are not exactly the same, but they are very similar, meaning that the predictions that you get, although you use different bootstrap samples, these bootstrap samples are very similar, so the predictions are also very similar, meaning that you are stuck with this erratic behavior coming from the data. How do you get rid of this non-smoothness, say? It's by combining very different data sets. Because maybe here we have this peak here because of the data, but if I then can use a different data set where you do not have this peak, or maybe that peak is not upwards but downwards, then aggregating these different views using different decision trees will smooth our function. The problem is that the datasets, the bootstrap datasets, are strongly correlated. They are very similar. And what we need to get smooth functions is datasets, bootstrap samples that are less correlated than what we have now. So what we need to decorrelate our bootstrap samples. What can we do? We can say, well, instead of taking this bootstrap sample and using all the data, I only use, say, 80% of the data. I create a bootstrap sample not with 100 observations, but with 80 observations. Why is that? Because if I have less observations in my bootstrap sample, then two different bootstrap samples have more room to be very different from each other. So that's a way to decorrelate the bootstrap samples. And let's run the code again to see what kind of function we get. And what you see is by decreasing the number of observations, we get still not a really smooth, but a smoother function. So let's decrease a bit more. But if we use less data, we can also increase the number of trees that we aggregate. And now you see with 40% of the observations, I get a much smoother function. And let's do one more check and use only 20 observations. Increasing again the B. And what we see now is that now we have a quite smooth function, which is a reasonable approximation of our green function. How did we achieve this smoothness? By decorrelating the bootstrap samples and the predictions. And how did we decorrelate? By using fewer data points in our bootstrap sample.